Dear students, grade 12. In today's lesson, we're going to complete the previous lesson about the equilibria. Okay, let's just check these learning outcomes. Last time we studied how to work the pKa, and we also learned about the 4 curves of titration. Okay, let's take a fast look. These are the 4 curves of titration. Can you remember this one? This is between strong acid and strong base, and actually the equivalent point will be equal to 7. Okay, strong acid and strong base. And here is between, if just take a look, it's less than 7 here. So if it's less than 7, this means that it's a strong acid and a weak base. This one, it's going up than 7. This means that it's a strong base and a weak acid. And same here. If it's between a weak acid and a strong base, of course, it's also more than 7. And we said we cannot determine exactly the equivalent point between a weak acid and a weak base. Okay, now what is an equivalent point? What does the term equivalent point mean? The equivalent point means the point in which an exact volume of base has been added to just neutralize the acid, or vice versa. If you're adding a base to an acid, it's the exact volume of base that you added just to neutralize that acid. And if you're adding the acid to base, so that means it's the exact volume of acid added to neutralize the base. Okay, so when we talk about neutralization, we have to know exactly what happens to the pH, okay, around the equivalent point. Okay, so here's the question. What generally happens to the pH of solution around the equivalence point? Of course, it does change, but there is a large and rapid change in pH except for weak titration, means weak acid, weak base titration. That's why we cannot determine it exactly. Okay, for a titration reaction, there is an end point. An end point, what is the meaning of end point? At the end point, the volume of acid and or alkali added, if you're adding an acid or an alkali, when an indicator just changed the color. So in titration reaction, we know that this is a reaction between acid and base. So when you're making a titration reaction, you're using whatever. If you're using an acid, you add the indicator, which is the chemical substance that changes its color when it reacts with acid or base. So if you're using the acid and you put the indicator, it changes its color according to if it's acid or base. So at the end point, you have the substance, whether it's acid or base, and you're adding the other substance using an indicator. So the end point is the point at which the acid or base change their color, of course, with the indicator. So if the right indicator is chosen, this means that not any indicator can be used in titration reactions, because we have seen that there are 4 types of titration reactions. We have weak acids with weak bases, and this one we cannot determine. We have weak acids and strong bases, weak bases and strong acid and base. So for each of these reactions, you have to choose the right indicator. And the right indicator at the end point actually change its color. So at the end point, actually the equivalent point is equal to the end point. So to make it simple, the end point is the point at which the acid or base changes its color if the right indicator is chosen. And at that point, the equivalent point is equal to the endpoint, that if you use the correct indicator for the reaction. Okay, this you have studied very long time ago. What is meant by an indicator? An indicator is a chemical substance that changes its color when it reacts with acid or base. That's an in general identification or definition of indicators. But what is, just a minute ago we said that we have to use the correct indicator for the action, the suitable indicator for the reaction. So what are the properties of good indicator for the reaction? How can you tell this is the suitable indicator? First of all, it has to have a sharp color change, not gradual. Means you can instantly just identify that there is a color change. No more than one drop of acid or an alkali needed for color change. So this doesn't have to gradually change, just an instant change, instant sharp color change using just one drop of acid or an alkali. The endpoint. The endpoint must be the same as the equivalent point, or titration gives wrong answer. So this means that the endpoint has to be the point in which the indicator changes its color, the neutralization or the equivalent point. Okay, otherwise it's wrong answer, so it's not the suitable indicator. Distinct color change, so it is obvious when the endpoint has been reached. Again, with the color has to be distinct, means obvious, clear, shown, just to show the endpoint has been reached or the equivalent point. This means that for every titration reaction between acid and base, whether they're strong or weak, both of them or either of them, this means that you have to use a definite or a suitable indicator. For example, this is a list of the 4 indicators, the 4 titration reactions, and the suitable reaction for each of them. For example, what indicator would you use for a strong acid and a strong base? If you have a strong acid and a strong base, so you need, just like we said, a distinctive change of color just using one drop, an instant change of color, and the equivalent point has to be the endpoint. So if you're using strong acid and strong base, you can use phenolphthalein or methyl orange. But usually they use phenolphthalein because it's clearer in color change. So this is the perfect indicator when you're reacting strong acid with a strong base. You use phenolphthalein because it has a clear change of color. What indicator should you use if the titration between strong acid and weak base? You can use methyl orange. What indicator would you use for strong base and weak acid titration? Phenolphthalein. So actually, this is one thing. Phenolphthalein is used in strong acid and strong base because it has a clear change of color, and it's used when you're using strong base and weak acid. For a reaction or a titration between strong acid and weak base, we use methyl orange. But last titration, this is the difficult one. When you're using weak acid and weak base, neither methyl orange or phenolphthalein is suitable. Why? Because neither of them give a sharp change of color at the endpoint, so you cannot actually determine the equivalent point. So again, just to make it simple, just to summarize, you have 4 different types of titrations for strong acid and strong base, and we said for each of them you need a suitable indicator which shows a clear change of color at the endpoint, and the endpoint should be equal to the equivalent point. So for these 4 titration types, Each of them have different indicator. So if you're reacting or the titration that you're making strong acid and strong base, you use phenolphthalein rather than methyl orange because it has a clear change of color. If you're using strong acid with weak base, use methyl orange. For strong base and weak acid, we use again phenolphthalein. And if your titration is between weak acid and weak base, you cannot use either because it does not give a change of color, a sharp change of color at the end point. Okay, now let's see that. What color is methyl orange in acid? Okay, this you have known before. We said that an indicator is a chemical substance that has distinctive or different color when it reacts with acid and base. So for methyl orange, this is one indicator. We said we use it when we're using strong acid with weak base, right? So methyl orange actually turns red, in acid. It's red in acid and yellow in alkali. So again, it's red, turns red when it's added to acid and yellow when it's added to alkali. The change at about 4 to 5, approximately same as the pKa value of the indicator. Now about phenolphthalein, the pH of methyl orange is from 4 to 5, okay? What color is phenolphthalein in acid and alkali, and what pH does it change? Okay, so the change in pH when you're using methyl orange is from 4 to 5. That's why we use it when we use a strong acid. Okay, that's why it's preferred when we're using strong acid plus weak base. Okay, for phenolphthalein in acid, it's red, colorless in acid, and red in alkali. The change that the phenolphthalein needs or makes in the pH of the solution in titration is between 9 and 10. That's why we use it when we're using strong base plus weak acid. So again, methyl orange, red in acid, yellow in alkali. It makes the pH in titration changes from 4 to 5. Phenolphthalein is colorless in acid and red in alkali, and it makes the change in phenolphthalein from 9 to 10. Now we're going to study about the buffer solution. What is a buffer solution? A buffer solution is a solution that resists the change in pH when small amount of acid or alkali is added. So actually it works against the pH. Okay, it makes sure that the pH does not change as much. So we have two types of buffer solution. For example, we have acidic buffer solution. What do acidic buffer solutions contain in general terms? Acidic buffer solution actually is a weak acid and soluble salt of that acid that fully dissociates. Dissociates means completely ionizes. So to write the reaction about acidic buffer, write the reaction between acidic buffer and with added acid. So A plus H gives HA. Oppose the addition of H. In this case, this is the reaction between the acidic buffer and when it's added to an alkali. When it's added to an alkali. And what do we mean by basic buffer solution? Weak base, also soluble salt of that weak base. This is our lesson for today, and see you next time.